Afternoon, boys and girls, on a very beautiful Saturday. It's quite hot actually this side. I'm quite warm and I'm really enjoying the weather. I hope that you are too and you are ready to enjoy yourself in another lesson on Technical Sciences Grade 12. And today we are dealing with momentum and impulse, and it's actually our last lesson on this topic, and it's a question and answer session. So I was expecting that you'd actually forward me some questions so that I'm able to assist you in the questions that you are struggling with or the concept itself. But since I didn't get any questions, then I am going to give you the questions today that we are going to treat. And I managed to get a couple of questions from various provinces as well. And they are really standardized questions. They are long, they are structured, and they're definitely going to help us concretize our knowledge of momentum and impulse. Then, in our overview, basically today it's momentum and impulse questions everywhere throughout up until the end of the session. So we will be dealing with these questions, and remember now, these questions we also use them to teach ourselves, because in a particular question, then there are issues that one can actually emphasize to you, and also by yourself as you do these questions, you can integrate your knowledge of momentum and impulse. So that is essentially how our lesson is going to proceed today. So this question is actually a question from the Northwest Province from 2019, and it's a very nice question actually, because it really encompasses the entire concept on momentum and impulse, especially with what you are definitely expected to know as per your examination guidelines. Now, let us read the question. It says, study the diagrams below which show okay, just want that to move. Which show a 150-gram tennis ball striking a wall at 20 meters per second. So there we actually have 150 grams of that tennis ball, and it strikes a wall at 20 meters per second and bounces back in the opposite direction at 16 meters per second. The tennis ball is thrown at a wall at right angle. So basically, this is what we see. We have our brick wall, and then we have a tennis ball, and the mass of the tennis ball, and I don't know what's happening there with Zoom. It's actually just hiding my value there, but I'll write it there for you. So there I have a 150-gram tennis ball, and it is going towards the wall. It was thrown towards the wall, and before it collided with the wall, it had an initial velocity of 20 meters per second. And then it hit the wall. After hitting the wall, then it moved at a velocity of 16 meters per second, and then it moved away from the wall altogether. And it makes sense why it would move away from the wall, because the ball, when it exerts a force on the wall by the time of collision, then the tennis ball is exerting a force that is going to the right on the wall. and the wall will exert a force that goes to the left on the tennis ball. So essentially, that is what is happening, and we've been given the velocity before the collision and the velocity after the collision. Then we are required to define the term impulse in width. Time the net force acts on the object, and that product is what we refer to as the impulse altogether. So we go there. Impulse is the product of the net force acting on the object and the time the net force acts on the object. Now, my dear learners, we can see there that it is 2 marks or 0. It means you can't get 1 out of 2. It's either you get all the marks or you don't get any mark. So it is 2 marks or nothing. In other words, everything there, my dear learners, must be correct in order for you to be able to obtain the 2 marks. So you cannot miss any keywords on that particular definition of impulse for you to be able to get the 2 marks altogether, right? So impulse is the product of the net force acting on an object and the time the net force acts on the object. Then we go to 3.1.2. We are then required to calculate the impulse on the ball. So we must get the impulse. And to get the impulse, we know that formula is actually going to be relevant, where we say F net delta T is equal to delta P. And this F net delta T, we definitely know that it is equal to impulse. In other words, impulse is definitely going to be a value that is equal to the change in momentum. In other words, if I want to calculate impulse, I can calculate it in 2 ways. The first thing is I can actually take the value of the net force, and then multiply it by the contact time. Then I will get the value of the impulse. Alternatively, if I don't have the value of the net force and the contact time, then I can get the value of the change in momentum. And when I get the value of the change in momentum, then I am definitely sure that I have the value for what? For the impulse altogether. So in this particular instance, we can see, we know the mass of the ball, which is this one, to be 150 grams. We know the velocity after, or rather this one is before the collision, and then we know the velocity after the collision with the wall. In other words, we know the value of M, we know the value of VI, and we know the value of VF. So we can actually calculate the change in momentum. And when we get the value of the change in momentum, then we are definitely sure that this value of the change in momentum is our impulse. Why must we go for that particular option? Because we don't know the net force that is acting on the ball, and we do not know the contact time with which the net force is acting on the ball. So we don't know for how long the net force was acting on the ball. So we can't opt for actually saying impulse is F net multiplied by delta T, because it won't assist us in terms of calculations for now. But what will help us in terms of calculations will be getting impulse as being equal to the change in the momentum of the ball. Right. Then we go to 3.1.2. Then let us take towards the wall as positive. Now, we know that when we take F net and we multiply it by delta T, we definitely know that it will give us equal to delta P altogether. Now, this is exactly what this formula is saying, because when you see F net you say F net delta T is equal to delta P. Altogether, my dear learners. Right. Then we say, okay, because we are using this one, right? So I just wanted to show you that this one is also relevant. You will get a mark. So let us continue with this one. Basically, we are going from this one to that one. So impulse is equal to M into Vf minus Vi. Then impulse is equal to the mass of the object. Remember, it was 150 grams. Now, if it is 150 grams, what we need to do is to then convert that grams will give us 0.15 kilograms altogether. So we need to take that mass in grams, divide it by 1,000, then we will have our mass in kilograms. Why do we want it in kilograms? Because we have to substitute it on the formula in kilograms. We cannot substitute it on the formula in grams. Into Vf minus Vi. Then my Vf, remember, that is the velocity after the collision with the wall. Now, after the collision with the wall, the final velocity is 60 meters per second. And remember, it was going away from the wall. So away from the wall will be negative. Minus, remember this minus comes from the formula. Then the initial velocity is the velocity before it collided with the wall. And it was 20 meters per second. And we substituted as positive because we said we are taking towards the wall as positive. Then you do your mathematics. You will then say impulse is equal to negative 5,4. Then when you see that it is negative 5,4, you then interpret it altogether. When you interpret it, you basically try to explain to us what the negative means. Then we say impulse is equal to 5,4 Newton second. Remember, this is the SI unit for impulse. And the negative means away from the wall altogether. How were the marks allocated? 1 mark was the formula. 1 mark was for the correct substitution of the mass, which has already been converted to kilograms. and then the substitution of the change in velocity that took place, which is Vf minus Vi. And the final mark is actually for the magnitude together with the direction. Remember, my dear learners, if you just wrote the magnitude, then you won't get a mark. If you just wrote the direction, you won't get a mark. But if you write both the magnitude as well as the direction, then you will definitely get a mark. So that will then give you 4 marks altogether. Right. Remember, my dear learners, there we've been asked to calculate the impulse, right? So you can't only give us the magnitude, you also have to give us the direction, right? Let us go to the next question on 3.2. Right. A car of mass 1,000 kilograms travels with a velocity of 33 meters per second and collides head-on with a truck of mass 2,000 kilograms, of rather 2,500 kilograms, that travels with a velocity of 19 meters per second due east. After the collision, the car and the truck move together respectively. Now, let us look at the diagram and actually see if what we have read there actually goes together with what we see on the diagram. So we've been given a car, it has a mass of 1,000 kilograms. There we see the car has a mass of 1,000 kilograms. And it was traveling at a velocity of 33 meters per second. And we can see that. And it collides head on. So the truck and the car, they are facing each other. So it's a head-on collision. And it is with a truck of mass 2,500 kilograms. There we see the mass, it's 2,500 kilograms. And the velocity of the truck is 19 meters per second. And we can see that 19 meters per second. And we've been told that it is due east. So my dear learners, what you need to realize there as well is that our direction here is used as east. And automatically it means this particular direction will be west. In other words, in calculating and giving direction, we can't then talk about right and left. We need to use the direction as given in our scenario. And in this case, we are talking east and we are also talking west altogether. So don't use to the right and don't use to the left, because we have been told that it is east and it is also west. Then in question 3.2.1, you are required to then state the principle of conservation of linear momentum in words. So we have to state it in words. And we know well this particular principle, which states that the total linear momentum of an isolated system remains constant in magnitude and direction. The total linear momentum of an isolated system remains constant in magnitude and direction. So if the system is isolated, then the total linear momentum will be conserved, or basically it will be remaining constant. And that is 2 marks. Let us see how we mark that particular question. It reads, the total linear momentum of an isolated system remains constant. or another learner could say is conserved in magnitude and direction, and that is going to give you 2 marks. You can see again, my learners, that this is 2 marks or nothing, so you cannot make mistakes on there. It has to be totally correct for you to get all the marks. So let us really use our examination guidelines to learn these particular definitions and to learn how to state the principles. Right, then let us go to 3.2.2. I really hope that you are still following. Now, you are required to calculate the speed of the system immediately after the collision. Now, my dear learners, I know that you know momentum to be a product of the object mass and its velocity. So you know momentum to be the product of the object mass and the velocity. However, remember there is a time when the velocity of an object is actually equal to the speed. It's just that with velocity, you will be giving us direction. But if we just say speed, it means you can give us the magnitude. So this basically means you can actually go and calculate the velocity, and that velocity, when you are not giving it that direction, it's similar to just giving us the value of speed. So when we say the speed, remember, in this particular concept, by the way, when you will be applying the principle of a minor technicality there, but we are back. So we were on 3.2.2, and we are being required to calculate the speed of the system immediately after the collision. Now, if we want the speed of the system immediately after the collision, then we must actually calculate the velocity, right? Because we are going to use the principle of conservation of linear momentum, and you know that to be the velocity on that particular formulae. But here, you know, the velocity, the magnitude of the velocity, in fact, putting it more correctly, so the magnitude of the velocity, it's actually equal to the speed. So when you want the speed there, you actually want the magnitude of the velocity, because then you are not going to give us direction. Why? Because when we talk about speed, then we know that speed is a scalar quantity. It is not a vector quantity. So we'll apply the principle of conservation of linear momentum, right? Let us get to it. There we go. So let us take east as being positive. Then if we take east as positive, then we know that The total linear momentum before the collision is equal to the total linear momentum after the collision. So the T there actually stands for the total. So the total linear momentum before the collision is equal to the total linear momentum after the collision, which is the momentum of object 1 plus the momentum of object 2. And our object 1 here is the truck, and our object 2 is the car, is equal to, after the collision, the momentum of the truck plus the momentum of the car. But this will be final. So the F there is for the final, the I there is for the initial. And then we take these two formulae, we break them down. When we say the total linear momentum before the collision, then we are talking about the mass of object 1 multiplied by the initial velocity of object 1. That is supposed to be a 1 there, plus the mass of object 2 multiplied by the initial velocity of object 2. So basically we are adding the momentum of object 1 and the momentum of object 2 before the collision. It will be equal to, after the collision, remember, they were moving together as a unit. The truck and the car were moving together as a unit. So they have the same final velocity after the collision. And that is why the final velocity there, it's taken out as a common factor. So when you take the velocity out as a common factor, then you are going to then have the mass of object 1 plus the mass of object 2, and that is going to be in brackets. Now remember what I said to you. I said our object 1 in this case will be the truck, and our object 2 is going to be the car. So let us go to the momentum. I'm substituting into this formula now. The momentum of the truck. Then the mass of the truck, remember, it was 2,500 kilograms altogether. And we are happy because it's in kilograms, multiplied by, before it collided with the car, it was moving at a velocity of 19 meters per second east. And because east is taken as positive, then that becomes a positive value, which is positive 19. Plus, now we get to the momentum of object 2, which is the car. And the car was moving, rather had a mass of 1,000 kilograms. And before it collided, it was moving at 33 meters per second, but then it was moving east. So it was due east. And because it was due west, it was moving to the west, right? And because it was moving west, then we have taken east as positive. It means west is taken as negative. And that is why the car, which was due west, is moving in the negative direction. And this will be equal to, now we are checking after the collision. After the collision, the mass of the truck was still 2,500 plus the mass of the car, which is actually 1,000 altogether, right? So that becomes 1,000. So if you do your mathematics then, you will see that 2,500 and you multiply that by 19. It gives you 47,500. And then you take 1,000, you multiply it by negative 33. It will then give you 3,300. Rather, it will give you 33,000. So that will then mean you'll take the 47,500, which is positive. You will subtract that to 33,000, and that will give you 14,500. And then when you get to the other side, you say 2,500 plus 1,000, then it will give you 3,300 altogether. So there, my dear learners, it is just a typo there. That is supposed to be 1,000. Remember, the mass of the car is 1,000. The mass of the car is 1,000. But when you go further, you can see this is based on the fact that that value is 1,000. That is why there we get 47,500 plus this multiplied by that, it's negative 33,000 is equal to 2,500 plus 1,000. Remember, that one will then give you 3,500. So there you can definitely see, because of that error, instead of being 1,000, it is 800. So you rectify that and you make that 3,500. Then you will say, okay, 47,500, you will then subtract 33,000. That will give you 14,500. And you will take that, you will divide by 3,500. When you divide that by 3,500, then this value is going to be 4,14 meters per second. And when it is 4,14 meters per second, it is still a positive value, so it will be due east altogether, because you also have to be able to round off correctly. But this part there where we say due east, it's not necessarily a value, rather it's not necessarily information that you have to indicate there. For what reason? Because we just wanted the speed, and the speed is a scalar quantity, so it does not have direction. So even if you don't include direction there, you will not be penalized, because we did not ask for the velocity, we asked for the speed. So if we ask for the speed, then you give us only the magnitude. Are we together? Right. So this is very critical, my dear learners. Hence, I was telling you that interrogate what you see, because I know that you have access to these marking guidelines, and if you take things as they are as well without checking, then you will then have problems. You see there, my dear learners, it's not supposed to be 800. It's actually supposed to be 1,000. So that value then becomes 3,500. That value becomes 3,500. Then to get the final answer now, you take 14,500, you will then divide by 3,500. That will then give you 4,14 meters per second. Are we together? Right. Then we move to the next question. The next question says, by means of calculations, show whether the collision is elastic or inelastic. Now, my dear learners, let us remind again ourselves. What do we mean when we say a collision is elastic? And what do we mean when we say a collision is inelastic? Now, you will remember very well that if the collision is elastic, the total linear momentum is conserved, as well the total kinetic energy is conserved. What does that mean about an elastic collision? It means the total linear momentum before the collision is equal to the total linear momentum after the collision. Then, if the collision is inelastic, then it means the total linear momentum before the collision is also equal to the total momentum after the collision. But what is the difference between the two? If it is elastic, the total kinetic energy before the collision will be equal to the total kinetic energy after the collision. But if it is inelastic, the total kinetic energy before the collision will not be equal to the total kinetic energy after the collision. So what does this tell me? To put it simply, what is similar about elastic collision and an inelastic collision is that in both elastic and inelastic collisions, the total linear momentum is conserved. But the difference is, in an elastic collision, total kinetic energy is conserved, but in an inelastic collision, total kinetic energy is not conserved altogether. So in trying to show whether a collision is elastic or inelastic, we must actually go and check what was the total kinetic energy before the collision and what was the total kinetic energy after the collision. Then we will look at those total kinetic energies. If we see that the total kinetic energy before the collision is equal to the total kinetic energy after the collision, then we will say the collision is elastic. But when we look at the total kinetic energy before the collision and the total kinetic energy after the collision, and we see that they are not equal, then we will conclude that the collision is inelastic. Now, let us go to that particular question. Right, so we start there. We want the total kinetic energy before the collision. Or another learner could say, it is the sum of the kinetic energy before, and that will be equal to the kinetic energy of the truck plus the kinetic energy of the car. And this must be before the collision. And we know that kinetic energy is given as half mv squared. Altogether, it is given as half mv squared. It means it's that divided by 2, it is that divided by 2. But you can simply keep it as half mv squared. Then before the collision, the mass of the truck was 2,500. The initial velocity of the truck was 19 meters per second east. And remember this, we have to square it because it's v squared. Now here, my dear learners, you don't substitute direction. This is actually a velocity that is equivalent to the speed. And we take it as speed because kinetic energy is a scalar quantity, and hence I don't substitute direction there. Divided by 2 plus, for the car, the mass of the car is 1,000. The initial speed of the car is 33 meters per second, and it is squared divided by 2, right? And you find that it gives you 995,750 joules. Now, this is the total kinetic energy before the collision. Now, let us do it for after the collision, and you can see that these calculations, you do them separately. After the collision, you will still do the kinetic energy of the truck plus the kinetic energy of the car. Then it is half mv squared. In other words, it's mv squared divided by 2 plus, for the car, it's mv squared divided by 2. So that's half mv squared basically. Then we say the mass of the truck is 2,500 multiplied by the final velocity of the truck. Now, the final velocity of the truck, my dear learners, you will remember that we corrected that value and we found it to be 4,14 meters per second. So you will take the 4,14 meters per second and you will square it out together, and you won't be using 4.39 because this was actually incorrect from the previous question. We recalculated and we found that it is 4,14 meters per second. So when you do your calculation, it will then give you 2,500 multiplied by 4.14 squared divided by 2. Right. So that gives us 21,424,5. Plus, we go now to the kinetic energy of the car. The mass of the car was 1,000. The velocity of the car after the collision, it's still 4,14 meters per second because we corrected that from the previous one, the previous question. So it's 4,14, and remember you only square that. You divide that by 2. Then you will say, okay, that will give me 4,14 squared, and that must be multiplied by 1,000, and we must divide it by 2, and that will give me 8,569,8. Then to get the total kinetic energy, you will add that to the kinetic energy of the truck. And remember the kinetic energy of the truck, it was 21,424,5. And in total, you will get that it gives you a total kinetic energy after the collision of 29,994,3 joules altogether. Then we'll say, oh, there's the total kinetic energy before the collision and there's the total kinetic energy after the collision. And we can see that they are not equal. And if they are not equal, what does that tell us? It tells us that the collision is inelastic. And for the final mark, my dear learners, is for you telling us that the sum of the kinetic energy before the collision is not equal to the sum of the kinetic energy after the collision. As a result, the collision is inelastic. So you wanted to prove that the collision is inelastic. Hence, you calculated the total kinetic energy before and the total kinetic energy after. But then you are forced at the end to make a statement there that gives a conclusion to this particular calculation. And the conclusion is by comparing the two kinetic energies. And because they are not equal, the total kinetic energy before is not equal to the total kinetic energy after, then we can conclude that the collision is inelastic. Right, so that is 3.2.3. This is a very important question. You will get it. They will definitely ask you, and you must be able to work with that all together. Right. Then let us go to 3.2.4. They tell us the car was fitted with an airbag. Explain how the airbag reduces the fatal injuries on a driver. Number one, my learners, we know that if a car is without an airbag, it is more likely that the injury is going to be more fatal. It will be deadly altogether, depending on the force that will be experienced during the time of the collision. So, when we have an airbag, we then know that we are actually more protected. And we must ask ourselves, what do we mean when we are actually saying that we are more protected? Remember now, during a collision, if you want to be safe in a car, right, or for you not to have a fatal or what we refer to as a deadly injury, is for you to experience a smaller net force during the collision. So if the force that you're experiencing during the collision, if the net force that you experience during the collision is large, and okay, let me put it this way. If during a collision, the net force that you're experiencing is large, then it's more likely that the injury will be fatal, or rather it will be more fatal. But if during a collision you experience a net force that is less, then the injury will be less fatal. So what does it tell me about airbags? It tells me that airbags must be having something to do with decreasing the net force that you experience during a collision. Because with an airbag, the chances of a death are small. We are not saying that they are not there. They are still there, right? They get smaller with the fact that you are actually having an airbag. So because of the airbag now, then it tells me that the airbag has something to do with ensuring that the net force decreases. In other words, if the airbag is not there, then it means the net force becomes high and hence the injury becomes fatal. But if the airbag is there, then the net force becomes smaller and the injury becomes less fatal. So the question is, how does this airbag decrease the net force? So we then need to check the relationship between the variables of what can actually cause the net force to decrease. Right. So when you look at this formula, F net delta T is equal to delta P. The contact time between the driver and the airbag will be longer, while the change in momentum remains constant. This effect will reduce the net force. Now, my dear learners, if I wanted the value of F net and I wanted to make F net the subject of the formula, then I will see that F net is equal to delta P divided by delta T. So my F net will be equal to delta P divided by delta T. Now, if F net is delta P divided by delta T, then it tells me that the relationship between F net and delta T is inverse proportionality. And if it is inverse proportionality, it means if the contact time increases and the change in momentum remains the same, then it means the net force is going to decrease, because the net force and the contact time are inversely proportional to each other. So if the contact time increases, then the net force is going to decrease, but for the same change in momentum. Remember now, two variables cannot, if the contact time is changing, then the net force will change, but the change in momentum must be our fixed variable. It must remain constant. And hence we are saying, if the contact time increases for the same change in momentum, then we expect the net force to decrease altogether. So what does this tell me? It tells me that this is exactly what an airbag does. It will increase the contact time for the same change in momentum and thereby decrease the net force. So that's exactly what will happen. So it says, according to the formula, F net delta T is equal to delta P, the contact time between the driver and the airbag will be longer. So the airbag increases the contact time, while the change in momentum remains constant. And this will definitely reduce the net force. So that is essentially how airbags work. They increase the contact time for the same change in momentum and thereby decrease the net force. Are we together? Right. So that was question 3.2.4. Right, we continue. Now, this is a totally new question, and this is a question from the Free State, from a test that was written in March 2020. And let us see what this question has in store for us. So I hope that you are still following, and please remember that you can still send your questions to the email that I always provide you with, and as I get the questions, then I will be able to assist you with your specific questions. But in the meantime, we will continue with the rest of the questions. Then it reads as follows. The diagram below shows turbo running on a horizontal floor and jumps onto a stationary 1.3 kilogram skateboard. The skateboard and turbo combination moves forward at a speed of 3.5 meters per second. Turbo's mass is 37 kilograms. Ignore the effect of friction. So what is happening here, my dear learners? Remember, I taught you, I'm really expecting you that whatever that you have read there, you will be able to talk to it in terms of the diagram as well. So we have before the collision situation and we have after the collision situation. Excuse me. Now, you should be able to see there that before Turbo collided with the skateboard, he was moving. So he has an initial velocity. The initial velocity is not zero because Turbo is not stationary. Then we have the skateboard. And the skateboard, we were told that it was stationary altogether. So if the skateboard was stationary, it means it was not moving. And if it was not moving, then it means its initial velocity before the collision with Turbo is zero. After the collision, they move together as a unit. Now, if they move together as a unit, what does that tell me? It tells me that they have the same final velocity after the collision. They are moving together as a unit. and both of them together, their mass is 37 kilograms. Now, let us go to the questions. Is momentum a vector or a scalar quantity? Then we are asked to explain. Now, we know momentum is a vector quantity. This is a recall question. It's a remembering question. You must know by now. It is a vector quantity. Then we must explain, because it has both magnitude and direction. Altogether, it has both magnitude and direction, and it is a vector quantity. You know that because it is a product of the mass of an object and its velocity. So it is a product of a scalar quantity and a vector quantity. And because we are multiplying the mass with the velocity, which is the scalar with a vector, then we get a vector. So it is a scalar quantity. Rather, it is a vector quantity because it has both magnitude and direction. So this is how you'd have said it's a vector quantity. What is the reason? It has magnitude and direction. And there I was just explaining to you why it is a vector quantity. Then we are required to define the term isolated system in physics. By now we know, my dear learners, when we talk about an isolated system, we are talking about a system in which the net external force acting on the system is zero. It's a system in which the net external force acting on the system is zero. So that will be the definition for an isolated system, and that is for 2 marks. Then let's see how we mark it. So it's a system on which the net external force is zero. And you can see, my dear learners, it is 2 marks or nothing. Are we clear? It is 2 marks or nothing. In other words, if you omit anything on there, then we have a problem, because we can't give you 1 mark. It's either a 0 or it's a 2. So ensure that all the keywords for the definition are part of the definition as asked for you to obtain all the marks. Then we go to question 5.3. Name and state a principle that can be used to calculate turbo speed before he jumps onto the skateboard. Now, what principle can we use? We have an idea about the mass and the initial velocities before the collision. And we have an idea again about the mass and the velocities after the collision. So definitely a principle that will be relevant here will be the principle of conservation of linear momentum. Then the question is in 2 parts. We must name first. After naming, we have to state, and that is why it is 3 marks. If you don't read this carefully, you will just state and you will not name, or you will just name and not state. So here we are required to name and to state the principle that we can use. So we are saying it is the principle of conservation of linear momentum. And the principle says, okay, that will be 1 mark. And the principle says the total linear momentum of an isolated system remains constant. And again, we see that it is 2 marks or nothing. And what I like about the marking guideline there is that it has actually underlined all the keywords that must be there. And someone can easily just see that everything must actually be there in order for you to get the 2 marks. So it is 2 marks or nothing. Remember again, If you don't want to say it remains constant, then you could have just said it is conserved. Now, let me show you here. Can you see that we have what we call negative marking there? So if you gave the name of the principal wrongly, then we don't mark the principal. It's an automatic 0. So you must get the mark for the principle of conservation of linear momentum in order for you to get a mark for stating that particular principle. You can't give us the name of a wrong principle and actually state the right principle and we give you marks. It is impossible. And that is why if you just stated and you did not name, then you also forfeit all the marks. So let us be very careful with regards to that. Right. Then we move to the next question. And the next question is 5.4. Then we are required to use the principle you have named in question 5.3 and calculate turbo speed before he jumps onto the skateboard. Now, to get turbo speed, it's quite easy. Now, someone could say, but we were not given the mass of turbo, and that is true. It was not given directly. It was somehow given indirectly, because in the last sentence they are telling us that turbo's mass, or rather it's actually very clear, it's turbo's mass and it is given there as 37 kilograms altogether. And we've been given again the mass of the skateboard and we've been told that it is 1,3 kilograms altogether, right? Then we just go there and we say the sum of the momentum before is equal to the sum of the momentum collision. And remember that before the collision, it's basically the initial momentum, after the actually the final momentum. So there it was just used as the sum of the initial momentum is equal to the sum of the final momentum. Some of you are probably used to P total before is equal to P total after. That is still 100% correct. Then the initial momentum before the collision is the mass multiplied by the velocity, and that is for turbo, plus the mass multiplied by the velocity, and that is for the skateboard. And this on the left hand side is before the collision, and this will be equal to, after the collision, its mass still of turbo multiplied by the final velocity of turbo plus the mass of the skateboard multiplied by the velocity of the skateboard. And this velocity there, we can actually take it out as a common factor, because after the collision, turbo and the skateboard are moving together as a unit, so they have the same final velocity. So let us choose the original direction to be positive, right? The forward direction to be positive. So the mass of turbo before colliding with the skateboard was 37 kilograms. It was given there. The initial velocity of turbo, meaning before colliding with the skateboard or before jumping into the skateboard, it's a value that we don't know. So we substitute it there. And we don't give it direction, because when we solve it, we'll automatically get the direction. Plus, the skateboard, remember, when you take the mass and to multiply it by the velocity of 0, because it was stationary before the collision, then you will actually get your product of mass and velocity to be 0. It's equal to, here, because the skateboard and turbo were now one unit, we take out the velocity as a common factor. So when we take it out as a common factor in brackets, it means we must add the mass of Thabo to the mass of the skateboard. And that's what we have done. It's 37 plus 1,3. And our velocity is a common factor, which is 3,5. Then in total, it means when we get the initial velocity of Thabo before colliding with the skateboard or before jumping to the skateboard, then we see that it gives us 3,62 meters per second altogether. Now, why did we not give direction there? Because we were asked to calculate Thabo's speed. Remember, speed now, it's actually a scalar quantity. It only has magnitude. It does not have direction. So how did we allocate marks here? 1 mark is for the formula, any of those. Another mark is for the substitution of before the collision. Another mark is for the substitution of the system after the collision, and the final mark is for the correct magnitude of the speed. Remember, it does not have direction. And why does it not have direction? Because speed is a scalar quantity. Then we are being asked in 5.5, is the magnitude of Thabo's final momentum greater than, the same as, or less than the magnitude of his initial momentum? So we want to compare Thabo's final momentum to his initial momentum. And then in 5.6, we are required to explain our answer to the question in 5.5. So we must be able to explain the answer. Now, let us check. Thabo's mass after the collision, it's still 37 kilograms. And after the collision, we know the velocity that he was moving with is 3.5. Before the collision, 7 kilograms. But based on what we calculated, we saw that the initial velocity was actually 3,62 meters per second. Now, what does that tell me? The mass before the collision and the mass after the collision is the same. What is different is that before the collision, the velocity was high at 3,62 meters per second. And after the collision, the velocity was smaller, which was 3,5 meters per second. So when you take 37 and you multiply it by 3,62, then you will get a value for a momentum. But that value for a momentum will be bigger than a value for the momentum after, because there you will be multiplying 37 with 5. So you'll get a smaller momentum, and here it's 37 multiplied by 3,62, a larger momentum. And therefore, the final momentum is less than the initial momentum. And why is that the case? Because the velocity after velocity before the collision. We go to just check how it was marked, and our answer is less than. And what is the reason? The velocity or speed is less after the collision. So this refers to after the collision. So we revert back. In 5.5, we are saying the final momentum will be less than the initial momentum. And what is the reason? It is because the velocity, which is the final velocity, which is the velocity after jumping onto the skateboard, is less than the velocity before he collided with the skateboard. The velocity before he jumped onto the speed. Right, so it must be very clear. The mass here, my learners, was constant. So mass had no effect on the momentum. The velocity or the speed in this case had an effect on the momentum. Before the collision, before jumping onto the skateboard, we had a higher velocity. After jumping onto the skateboard, we had a smaller velocity. And that is why before jumping onto the skateboard, the momentum will be high. After jumping onto the skateboard, the momentum will be less altogether, right? And that is how you would have answered that particular question. And honestly, my dear learners, this is really not challenging. You just need more practice, and you will do very, very well. Now, let us move to the next question. The next question is a question on a rifle. Now, they tell us a hunting rifle fires a bullet horizontally to the left. The bullet leaves the barrel of the rifle at a speed of 965 meters per second. Due to this, the momentum of the rifle is 4.05 kilograms dot meters per second to the right. Now, let us analyze what is happening together with the diagram. Now, before the firing is what we will look into. After the firing is what we will look into. So let us check what was happening before the bullet was fired. Now, before the bullet was fired, the rifle is stationary. So its initial velocity is zero. Again, the bullet is inside the rifle and it is not moving before the firing. So its initial momentum must be zero. Now, we look at firing. So after firing, the bullet now leaves the rifle. So it moves at 965 meters per second. It means we have the velocity of the bullet after the firing. But what do we know about the rifle? We know that because the rifle exerted a force that is going to the left on the bullet, then the bullet will simultaneously exert a force on the rifle, and the force will be to the right. In other words, the rifle will do what we call recoiling. It will then move to the back. And you've seen when people shoot, the bullet immediately when it goes down, when it comes out of the rifle or a gun, any gun in particular, then it will, the rifle itself will then move backwards. And the backwards in this case, it will be to the right, and that will be for the rifle. But definitely then the bullet will move to the left. So we are required to calculate the mass of the bullet in kilograms. Now, when they say we must calculate it in kilograms, then we are not worried, because our formulas in paper 1, we substitute our mass in kilograms. In other words, when we are solving questions again, we will be getting the mass in kilograms automatically. We won't be converting. Themselves are giving us the mass in kilograms. What are we going to use in order to answer this particular question? Remember now, you might be understanding that we need to use the principle of conservation of linear momentum. Why? Because we are dealing with momentum. But when you get questions, you must be able to figure out that here I am dealing with momentum. And Why can I use the principle then? Because you have a very good idea about the masses as well as the velocities before the collision and after the collision. Here, very nicely so, they even gave us the momentum of the rifle after the collision, and they said it is to the right. Before the collision, it was not given, but we know that the momentum was zero because the object was not moving. So how would we answer that? We will apply the principle of conservation of linear momentum. Then we will say the sum of the initial momentum is equal to the sum of the final momentum. In other words, the total linear momentum before the collision is equal to the total linear momentum after the collision. But remember here, my dear learners, it's more like firing. So the total linear momentum before firing is equal to the total linear momentum after firing. So what can we say? Remember now, before these two, which is the rifle as well as the bullet, they were not moving. So the initial velocity is zero. And it is the same, and they were one system. So you can take out the velocity as a common factor altogether. And then you can add the masses in brackets. But remember now, you actually don't have the value of the masses altogether. But that is not going to hinder you. Why? Because anyway, you know that the initial momentum is what? It's a zero altogether. So that will be zero. After the collision, or rather after the firing, then it will be the mass of the rifle multiplied by the final velocity of the rifle plus the mass of the bullet multiplied by the final velocity of the bullet. Yes, we normally break it down, but here you didn't have to, because the mass times the velocity is the momentum itself altogether. So it is the momentum itself. And we were given the momentum of the rifle in this question. They told us that it is 4,05 kilograms dot meter per second to the right. Now, momentum is a vector, so we'll substitute it with direction. Firstly, for the magnitude, we know the magnitude is 4,05. But what about the direction? Remember, according to this, we chose to the to the left as positive. So if the left is positive, then the right is negative. That is why that value there is substituted with a negative, because the momentum was to the right. Plus, then we go to the bullet, the mass of the bullet there, which is what we are looking for, multiplied by the final velocity of the bullet, which is the velocity after firing. It is 965 meters per second altogether. And remember, it was going to the left, so it's a positive value, and hence it is substituted there as a positive. And therefore, the mass of the bullet, when you work it out, it will give you 4,197 multiplied by 10 to the power of -3 kilograms altogether. It's as simple as that. 1 mark for the formula, 1 mark for the substitution before the collision, 1 mark for substituting the final momentum of the rifle, 1 mark for working with the product of, or rather 1 mark for working with the momentum of the bullet, and 1 mark for the final answer with units altogether. 5 marks, definitely is that one. Then in question 6.2, we were asked to convert the mass of the bullet to grams. Now, we know that if we want to go from grams to kilograms, we divide by 1,000. So if we want to go from kilograms to grams, then we must multiply by 1,000. So here we want to go from kilograms to grams. So we have to multiply by 1,000. So the value for kilograms is then multiplied by 1,000. If you multiply this by 1,000, then you will get 4,197 grams. And that will be your mass in grams altogether. So in a nutshell, my dear learners, these are types of questions that you're going to get. And I really chose this question for you to remind you that you are not always going to be asked to calculate the velocity. You can also be asked to calculate the mass of an object, and you must be able to work with that altogether. Right. Now, let us discuss our examination tips before we conclude the lesson. A reminder again, this is going to be 22 marks. Actually, plus minus 22 marks, it could be 23 marks, 21 marks, you know, somewhere there. So be able to work with this topic in paper 1. Now, tips again, more and more tips. Number 1, my dear learners, in this particular topic, you must know your important definitions that we've been talking about here. And that is the definition of the term momentum, the definition of the term isolated system, the definition of the term impulse. Those 3 definitions are important, and it is 2 marks or 0. And there is only one principle that we are going to work with here, and is the principle of conservation of linear momentum. You must be able to state it. And all of those, you must be able to state them as the examination guideline is stating it. So you cannot go and give us the definitions and the principles that are in your textbooks. And remember, we are giving 2 marks or 0 for our definition. So in defining, ensure that all the keywords are there in that particular definition altogether. Secondly, you will get a formula sheet. And in your formula sheet, you will get formulae that fall under forces. And those formulae will include the formulae for momentum and impulse and so on. And you must be able to use that altogether. You will see that P is equal to mv. It's one formula that you will get. You will get delta P is equal to mvf minus mvi. You will get F net delta T is equal to delta P, and be able to use them. Again, my dear learners, you copy down the formula as it is from the examination guidelines. Furthermore, my dear learners, ensure that you give the correct units for every variable that you are being asked. So we were dealing with momentum. The units for momentum is kilograms/meter per second. The unit for mass is kilograms. The unit for velocity is meters per second. The unit for impulse, the SI unit, it's Newton second, Newton.second. And if you calculated it in terms of the change in momentum, then you can still use the unit kilograms/meter per second, because then it is actually a fact that you know that the change in momentum is equal to the impulse. But if you calculated impulse in terms of F net multiplied by delta T, then we are expecting you to give us the actual SI unit, which is Newton second. So be able to deal with that. When you are given your mass in grams, convert it to kilograms before you substitute it onto the formula. Again, when you are dealing with vectors, when you deal with momentum, when you deal with velocity, when you deal with net force, when you deal with impulse, those are vector quantities. So you must give us both magnitude and direction if we ask you to calculate those. Unless if we ask for the magnitude, then you don't have to give direction. With scalar quantities, for example, in this topic, your mass, your contact time, then you don't have to give us direction because they are scalar quantities. They don't have direction actually. So be able to read your questions in between. Are we clear, my learners? And make sure that you present your answers in such a way that you will be able to obtain full marks. And hence, I was showing you how to mark altogether, or perhaps how we mark you. And I know you are very technological learners. You are getting access to marking guidelines and question papers. Be able to do a question and mark yourself. And when you see that there's a bit of a problem, go back to your teacher at school or send me questions via our email so that I am able to help you with what you actually do not understand. And that will make it easier, because sometimes I know that when you go and check yourself after doing a question with marking guidelines, you find that there are problems and you don't understand and so on. So check with your teacher all the time. Check with me. I'm here for you at any time that you want me to help you. And if you want to ask more questions again, please send your questions to stemdigitalschool@africateamgigs.co.za, and I will receive those questions and I will be able to assist you. So I hope you have definitely enjoyed the lesson as much as I did, and I will see you on Monday when we treat another topic in technical sciences. Thank you so much and enjoy the rest of the afternoon. Goodbye.